is already co-host, co-moderator. Yes, so Ben will talk about the weak gravity conjecture and BPS particles. Please.
All right, can you see my screen?
Yes.
All right, thanks very much to the organizers for putting together this very nice workshop and for inviting me to speak. I'm going to be talking about the weak gravity conjecture, and it's not in my title, but really the sublattice and or tower weak gravity conjectures and how they relate to BPS particles. This is based on a work that should be done soon, hopefully, with Tom Rudelius and Murad Alim. This project has been going on for years, so hopefully will be done soon. But I'm going to tell you about the current status. And then I realized when I made this slide that this looks like some kind of occult symbol, but I'll explain what it is later. Okay, so let's start off with the weak gravity conjecture. Let me just state it this way. For every U1 photon in the gauge group of some quantum gravity, if I have a gauge group at low energies, there's a charged particle with charge to mass ratio bigger than or equal to that of an extremal black hole. And this, of course, is because we want sub-extremal black holes to decay. That's the motivation for the weak gravity conjecture. What I really want to talk about most is the stronger version, either the tower or sublattice weak gravity conjecture. So these date back to some papers with me and Tom and Matt Rees, and this more recent work by Gary Hsu and collaborators on the tower version. And the statement of this, without being too particular about the difference between these two conjectures, is that for every charge direction, at least every rational direction, so that a direction of charge that points to a lattice site, there should be an infinite tower of charged particles which satisfy Q over M bigger than Q over M in an extremal black hole with a parallel charge vector, right? So that's what we're supposed to compare with, is a black hole with a charge vector in the same direction. Okay, so why should these conjectures be true? Well, one motivation was that these conjectures are preserved under, well, at least tree-level dimensional reduction, whereas the weak gravity conjecture itself is not. Or it's easy to write down examples of, putative quantum gravities that satisfy the weak gravity conjecture, but then once you put them on a circle, then they don't. So presumably those are in the Swampland. But this criterion is fully consistent under putting on a circle or any other Ricci flat manifold. And so that's one motivation for considering it. Another motivation, which is a pretty strong motivation, is that the sublattice conjecture, which is the stronger of these two conjectures, is in fact a theorem in the tree level electric NS sector of string theory. So if I look at the at worldsheet string theory, in the NS sector, I have, for every gauge boson, there's a conserved current on the worldsheet. And so it's a question about global symmetries in the worldsheet theory. And using modular invariance, I can conclude that there's a tower of operators on the worldsheet that have, dimensions that go like their charge squared. Okay, well, there's an issue about how does that relate to an extremal black hole. That's something that's being addressed in another ongoing work with me and Matteo Letito that should also be done very soon. The older argument that there are operators that go with dimension like charge squared is due to these two papers, these simultaneous papers from 4 or 5 years ago. Okay, so all right, so we have very strong evidence in this perturbative context. And remember, this was also, this compactification argument was tree level, right? So we have all these arguments are kind of perturbative. So what we would like to know is the tower / sublattice conjecture true beyond perturbation theory? Now this is pretty hard to check. So we're going to fall back on our usual mainstay for non-perturbative things. We're going to look at BPS states, or in particular BPS particles. All right, so now many of you might object because it's commonly said that the weak gravity conjecture is trivial for BPS particles. Well, first of all, let me say that this is just not true. So let me explain why, and then we'll come back to the sublattice versions. Okay, so what is the weak gravity bound in comparison to the BPS bound? right? The weak gravity bound says that there should be some particle, at least one, with mass less than or equal to the mass of an extremal black hole with the same charge. Well, this is, by definition, this scales linearly with Q because we really mean like a large extremal black hole. We throw out all corrections in this statement. The BPS bound, on the other hand, says that the mass of all states in the theory must be bigger than or equal to the absolute value of the central charge. And this, again, this is something which is linear in Q, at least in Q in a certain direction. If you scale up the Q's, this scales up linearly. So these are kind of going in the opposite directions. And well, of course, an extremal black hole is a state in the theory, so that means that BPS particles are necessarily super extremal or extremal, because a BPS particle with the same charge as a black hole, since it saturates this bound, it must be at least as light as the black hole. So that means that they're either extremal or they're super extremal. Okay, so then we say, well, of course, if we have a BPS particle, then we satisfy this statement. So end of story. Well, not quite. So if we have more than one photon, so let's look at this situation here. Here I have a BPS bound over here and one over here. And this is the region where there are black holes. And I'm being very generous. I'm saying I have BPS states all the way along here and along here. But now if I take the convex hull of these BPS states, they simply don't cover the black hole region. So just assuming these BPS states would not be enough. Of course, if I put something way out here, then I could do this. But it's not a trivial statement. Okay, so in other words, one of the main points of this slide is that extremal does not imply BPS. So there are extremal black holes which are not BPS. That's very important to keep in mind. There's an example. This is actually a real example I pictured here. I haven't told you the details, but we'll talk about it a bit later in the talk. So there are real examples like this where I have extremal black holes that are not BPS. And actually those are very common. So that's important to keep in mind. So now let's get back to the Tower/sublattice conjecture. So the other thing that people might say is, well, in any case, it's obviously not true non-perturbatively because there's this simple counterexample. So basically the Tower/sublattice conjecture predicts infinite towers of BPS particles, but those don't always exist. So for example, if we look at a conifold geometry, so this is a conifold here, this is resolved over here. This is a singular conifold, and here's a flop of that resolved conifold. So there's two sides here. I can also deform to blow up the S3 here. And now let's do this in type 2A string theory. And now I can wrap a D2 brane on this small S2 here. And this gives me a single BPS state. I can't wrap it more than once. There's just not a BPS state for that. So there's just a single BPS state. And as I go to the singular point, this BPS state becomes massless. And if I go through to the flop, then it becomes massive again. Whereas if I go this way, then it Higgses the gauge field, a gauge field. So this is really the intersection of a Coulomb and Higgs branch for a U1 gauge theory. So it's a very simple thing to understand in effective field theory. It's maybe a little less simple to get at it from string theory because we have to think about this wrapped brane. Okay, but like I said, there's only one of these wrapped states. There's not another BPS state of charge 2 or another one of charge 3, etc. In fact, that would be very bad if there were, because these things are becoming massless, and then we would have an infinite tower of massless things. And that really just can't happen at finite distance in a theory of quantum gravity. So, all right, so there's not an infinite tower, so we've falsified these conjectures non-perturbatively. Well, that's not true, because this is simply not a prediction of the tower or sublattice weak gravity conjecture, not always. We have to understand when is this a prediction and when is it not. Okay, so let's give a simple example of why this is not always a prediction. Let's consider heterotic string theory on a circle. So here's the spectrum. Here n and n tilde are non-negative integers. And I have my left movers and my right movers in this level matching condition. All right, so there's a BPS bound, which is that alpha prime over 4m squared is bigger than or equal to half q right squared. It's very obvious that this is true because n tilde is a non-negative integer. There's also an extremality bound for black holes, and it looks like this. It has instead of this expression, it's got the maximum of q left squared and q right squared. So these black hole solutions have been known for a long time. You can look them up in the literature. So now let's look at a particular kind of state here where n and n tilde are both 0. Now these states are BPS because n tilde is 0. but they're not extremal because if you look at this left part here, the mass is half q left squared minus 1. So because of that minus 1, they're strictly super extremal. Okay, so let's look at a real example. Again, I'm going to take either the E8 times E8 or the SO32 heterotic string. I'll put it on a circle without Wilson lines just for definiteness. And I'm just going to look at those two directions coming from the circle. And I'm not going to do anything with the E8 times E8. Just so that I can draw this. There's two dimensions, I can draw them very easily. So this is what the spectrum looks like. These are the lightest states of a given charge. I didn't plot any of the ones that are heavier of the same charge. They would be farther in. And here on the left and the right, these are BPS bounds. And the red things are, the red particles here are BPS states. And the blue ones are not BPS. All right, so here you see the black hole region is a square. And these are all extremal BPS states on the left and on the right. But this guy up here is not extremal. He's strictly super extremal. And in fact, there's only one of these. Unlike over here, there's infinite towers of these guys. So it's the same kind of puzzle we just had. So let's ask, well, how can the tower or sublattice conjecture be true in this direction? Well, let's look at that direction. There's the single BPS state. But look, here's a bunch of non-BPS states down here. And there are an infinite number of these, right? They're still super extremal. Because this BPS state wasn't extremal, there's plenty of room between the BPS bound and the extremality bound to have non-BPS things that are extremal. And that's precisely what happens here. In fact, we knew it had to happen because of what I told you about the sublattice conjecture being a theorem. This is one of the areas where that theorem is applicable, right? We're just dealing with the NS-NS sector of string theory at tree level. So we knew this had to be true. That was just a question of finding out how it is true. Okay. Good, so now we have a refined prediction. So it's too glib to say that all BPS states come in infinite towers. Whenever we have a direction where BPS is the same as extremal, then we should have an infinite tower of BPS particles of increasing charge. So in this example, here's this cone where BPS equals extremal. And in this region, we should have infinite towers of BPS states. And indeed, from the heterotic string spectrum, you can easily see that you do. So everything is fine so far. So what we want to do now is test this prediction in a more non-trivial setup with a lot less supersymmetry. So the setup that I'm going to use is a 5-dimensional setup. I take M theory on a Calabi-Yau threefold. So this is very non-perturbative in a sense because we're not doing string theory anymore, we're doing M theory. Okay, so let's talk about what does the effective field theory look like. At low energies, we have, in general, 5D n equals 1 supergravity. And here's just the action for the vector multiplets here. And at a generic point in the vector multiplet moduli space, the gauge group is just going to be U1s. Any enhancement will happen at special points. So I'm just going to set a generic point, and I'm going to write down the action with U1s. And I'm not writing down the hypermultiplet action, just for simplicity. So this is what the action looks like. Everything in this action is controlled by this prepotential. This is a cubic polynomial in some formal variables yi. And the number of these i's, I didn't write this here, but this is the same as the number of these values of I is the same as h11 for the manifold. And in fact, these coefficients here are just the intersection numbers for the Calabi-Yau threefold. So there's very simple geometry here. And now how do we get this theory here? We take this slice f equals 1. And now we parameterize that slice by saying the y's are functions of scalars, just one fewer scalar than the number of y's. That's because the gravity multiplet doesn't have a scalar in it. So the number of y's is the same as the number of gauge fields, but the gravity multiplet has only a gauge field and not a scalar. And then we form this metric. This is the gauge kinetic matrix involving these derivatives of the prepotential. And then the scalar metric is just the pullback of that. And again, the Chern-Simons couplings are the third derivatives of the prepotential. And that's very important because Chern-Simons couplings cannot be field dependent. That's why this prepotential has to be cubic, because Chern-Simons couplings cannot be field dependent, otherwise there's a gauge anomaly. Well, it's not gauge invariant, right? So this prepotential is not corrected. It's very different than things that would happen, say, in 40 n equals 2 supergravity, where we can have lots of corrections. This prepotential is almost exact. I'll explain in a minute how it's not quite exact. So there's just one way that it can be corrected. Okay, so but first let's say we wanted to study BPS particles. So let me write down the bound for BPS particles here. I'm also writing the bound for BPS strings because if I had gotten farther in my talk, I would have said something about strings, but I think that I'll have to skip that for today. So let's just focus on the particle bound here. I have some central charge I'm calling zeta, which is just linear in these coordinates yi. Okay, so the one sense in which the prepotential can change is at phase transitions. So let's suppose that we have n hypers with charge q sub I, and in this part of the moduli space, q sub I, the central charge is positive, and in this part of the moduli space, the central charge is negative. So I'm assuming that I chose q such that there was a point where the central charge was 0 in the moduli space. Okay, so what happens? So this is in fact a flop of the geometry, and the prepotential will change. So the Cij, are different on the two sides of the flop. The intersection numbers change, and they change in a very precise way that's determined by the charge of the hypers becoming massless and how many of them there are. So there's just a very simple formula that tells us the only way that this thing can change, this prepotential. Well, there's one other thing that can happen, which is that if I have vectors becoming massless, then again, I'll have a change, but now with a minus sign here. It's very similar to the hypercase. However, this really only happens at boundaries of the moduli space, because this happens, say, when U1 enhances to SU2, and the Coulomb branch of SU2 is really a half infinite line, not a two-sided line, right? So this is actually happening at a boundary. Nonetheless, there is a sense in which these C's really change in this way, even though it's happening at a boundary. Okay, I won't go into that any further. So now what I want to do is I want to study black hole solutions to this 5-dimensional supergravity, and that's going to allow me to get at when are black holes supersymmetric and when are they not, right? That's gonna, then I'll know, once I know that, I'll know what the predictions of the sublattice or tower conjecture are. Okay, so I'm just going to study spherically symmetric black holes. Actually, it's a pretty hard problem to find non-spherically symmetric ones. So if anyone wants to try that, please do. But here are the spherically symmetric solutions. Okay, so I just have this simple ansatz. I'm not going to belabor the point. It turns out once you have this ansatz, you have to solve some equations that look like this in terms of this kind of inverse radial variable, z, which goes like 1 over r squared. Okay, and once you have a solution, the mass of the black hole involves the z derivative of this psi, which is in the metric, evaluated at infinity, which is the same as z is 0. Plus this contribution. This other contribution is going to go away when I have a so-called quasi-extremal black hole. In other words, a black hole with 0 temperature. I'm making the distinction here between quasi-extremal and extremal because extremal is going to be the lightest black hole of a given charge, and those are not quite always the same thing. Again, I won't go into that too much in this talk, but in general, they're not always the same thing. Okay, so how would we find these quasi-extremal or extremal solutions? So we can use this fake superpotential method due to these people, which is also, kind of an evolution of the attractor mechanism. I didn't write the people for the attractor mechanism on this slide. That goes back even farther. So suppose we have some function w of phi, and it happens to solve this partial differential equation here. This is a PDE on the moduli space. Why? Well, if we have this w, then these gradient flow equations, if I solve them, which is relatively easy to do, it will end up solving these second order equations. So this is kind of like a supersymmetry-like trick, although this doesn't have to be the central charge. And in fact, although I'm doing this in a supersymmetric theory, I could also do the same thing in a non-supersymmetric theory. Okay, so this is a way to solve the black hole equations. But when is this really a good solution, right? I really want a solution that has a horizon and not something with a naked singularity. Okay, so let's look at what could happen for different W's. Here's an example of a good W. It has a minimum here, and the gradient flow is going to take me down to the minimum. And if you study the gradient solution, you go back and you look at the metric ansatz, et cetera, what you find is that there's going to be a smooth horizon with a finite area. So everything is nice. Okay, here's a different W, this one down here, and this is going to give me a bad solution. This is going to give me a naked singularity. Well, why is that? one way of understanding it is that once I have W negative from those gradient flow equations, psi dot is positive. And maybe if you remember a slide or two back, the mass of the black hole goes like negative psi dot. So this is like a negative mass solution. We know those things can't happen. Okay, so then you just have to go and prove that they can't happen. Well, it turns out it's easy to prove that solutions with smooth horizons always have negative psi dot, and so this just can't happen. Okay, so this is kind of good and bad flows, and we want to know if for a given W, do we have a good flow? Then we can get a supersymmetric, or not just supersymmetric, we can get some smooth black hole solution. And if it's a bad flow, then we won't from that W. Okay, so if we have such a solution, then the mass is just simply related to W at the value of the moduli at infinity. Okay, so let's suppose that W is defined everywhere in the moduli space. Then it's a theorem that I'm about to prove to you that the black hole mass has a lower bound given by W with this normalization for all spherically symmetric solutions. Okay, so how do I prove that? There's kind of a trick to it. Basically, I write the mass, instead of writing the mass, I write it as this funny integral here. This is kind of something a little bit like an action, but it's not quite. And then I do some completing the squares in kind of like a typical like BPS kind of trick. And so then I have, since I have all these squares, those are non-negative, so I can write this as greater than or equal to this last term here, which I can evaluate, and I get the thing that I wanted to be the lower bound. Now the important point is that there's two steps here, this one and this one. I haven't fully written out these steps, where I'm using the fact that my solution has a smooth horizon. Because solutions without smooth horizons just won't satisfy this bound, but of course they're not physical. If I allow myself to have a naked singularity, I can have any mass that I want. Okay. All right, so this was just if W was defined everywhere, but now let's suppose that all the flows that W induces from any starting point are all good flows. So each one of those flows is going to give me some extremal solution. Well, that means because this with an equal sign was the mass of the quasi-extremal solution, that means that not only is this bound true, I can saturate it. And that means then this is in fact the black hole extremality bound when I have this situation where all the flows of W are good. So in this favorable circumstance, I can just determine the extremality bound by finding this W, all of whose flows are good. So that's what I'm going to do for you a little bit later in the talk. Otherwise, W just provides a lower bound on the black hole mass, but it's not a saturated lower bound. Okay, so let's compare this to what we know about BPS states. So it's easy to check, first of all, that if I put W equal to the central charge, then I solve this PDE. So that's good. I solve it everywhere in the moduli space, so that means that this bound is true, right? Just like I said, for any W that's defined everywhere in the moduli space. But this is obvious, this is just the BPS bound, right? So I haven't got any new information yet. What I really need to know is whether the flows for the central charge are good or not. If they're all good flows, then I'm going to have supersymmetric black hole solutions. But if I have a situation like this, then I won't. Right? If the central charge is going through 0, again, for the same reason as before, I will not have supersymmetric black hole solutions. In fact, typically there'll be some other W which is not BPS, which will give me the extremality bound. Okay, so let's go and try to solve this problem. We want to know, when do we have good flows? So it's just a bit of a pain to work with this F as 1 constraint. So let's step around it. Instead of taking F as 1, let's projectivize. So we're going to say that we identify our coordinates yi with lambda times yi. Right, so this is a perfectly good way to describe the moduli space in terms of some projective coordinates. So now I can write down a metric, and I'm going to choose the metric to have some non-zero weight. It's convenient to have the metric have weight -2. This is just continuation of this gauge kinetic function off the patch for all where F is 1. So then it takes this form, right? If I set F to 1, I had the expression I had before. But this is the same as the minus the second derivative of the log of F. So what that means is that minus log of F is a convex function because this gauge kinetic matrix has to be positive definite on the moduli space. So this minus log F is convex on the moduli space. So now I can write the central charge in terms of these homogeneous coordinates, I just have to put in an appropriate power of f to make sure that zeta doesn't have a scaling weight. I want to really write the physical central charge, not something that has some unphysical scaling. So now let's look at gradient flow for the central charge. So you can write down gradient flow just in terms of normal scalar field coordinates, but now if I write it for these homogeneous coordinates, it turns out to have a very nice form, kind of the obvious thing. You just replace your scalar fields phi with these homogeneous coordinates and everything works with this same A I had before. Okay. Now, these are still kind of hard equations, so let me make them even easier. I'm going to define dual coordinates. Dual coordinates have weight -1 relative, the coordinates had weight 1. The dual coordinates have weight -1, and they're basically the first derivative of this log of f. So this is basically like a Legendre transformation. We're going back and forth between like a coordinate and a momentum, kind of same idea, like a velocity and momentum, right? So in fact, because of the way that Legendre transformations work, that is telling me a very important piece of information, which is that there's a one-to-one map between the y's and the y tildes. How do I prove that? Well, look at this combination, y tilde y minus log f as a function of y. And now to find y given y tilde, I find the minimum of this function. Because if you put in the condition that you're at a minimum, you'll get back that y tilde is the y derivative of log f. But in fact, since this minus log f is convex, there's a unique minimum, if it exists at all. And so in fact, there's a unique y for a given y tilde, if there is one at all. So that tells me that there's indeed a one-to-one map between these coordinates. Was there a question? I guess not. Okay. So now let's write the gradient flow in these dual coordinates. Now something very nice is starting to happen, because you notice this term just depends on q. All right, so it's not so obvious yet, but actually I can integrate these equations. So the integrated equations look like this. The dual coordinate y tilde up to this e to the psi factor is wherever I started plus some term depending on z times the charge. In other words, I start at some point in the moduli space, and as z becomes big, when I get close to the horizon, then I get close to the dual coordinate being parallel to the charge. This is just some linear interpolation. So what that means is that gradient flows are in fact straight lines in these dual coordinates. If I wanted to write down, what function of z they are, well, actually, that's also easy here. But just to know, what path they follow, they're just straight lines in dual coordinates, and they're directed towards the point where the dual coordinates are proportional to the charge. So this is a very nice picture. Here's an example. So let this triangle be the region where the dual coordinates can take values in. It's not, all values. I'm going to call that k check. And here, in this case, outside that region is where the charges are. To make this picture, more physical and easier to draw, I've divided by one of the homogeneous coordinates in a usual kind of way for getting rid of my scaling. Okay, and then these flows are just going in a straight line towards that point. In this case, they don't reach it because it's outside the moduli space, but you know exactly which direction they're going because of what we found about the flows. But now let's suppose that the Q does sit inside K check. Suppose also that this region K check is convex. Well, I said I would argue later, but unfortunately it's not in my slides, but I can tell you a bit about how the argument goes. At least for a large class of geometries, we can argue that this is true, that K check is convex. Well, if that's true, then that means if Q is inside K check, then all the flows are good, because the flows just go from wherever they end up here. They don't, for instance, run into a boundary because the region is convex. And you can also easily check that the value of the central charge here is positive. So it's just a nice function with a global minimum, and it's just all the flows are running down to that global minimum. So this is a very nice situation, and I get smooth BPS black holes from this situation. So what that means is now I have a prediction. If Q sits inside K check, then there should be an infinite tower of BPS states. So in other words, for all directions inside this region of dual coordinates K check, there should be an infinite tower of BPS states. The only technical assumption here is that this K check, I'm assuming, is convex. If not, then I have to worry a little bit about what if the flow runs into the boundary. So otherwise, this is a sharp prediction of the tower / sublattice conjecture. This I can't get around. So let's see if it's true or not. So let's take an example. Let's look at a particular caveat, which is the complete intersection of 2 degree 4-1 polynomials in this weighted projective space here times P1. Okay, well, why do we write down this example? Well, it just happens to have a nice property that there's 2 phases related by a flop, and these 2 phases happen to be the same caveat. So it flops to itself. That made it a lot easier to think about back in the day. It also happens to avoid a little bit of a bugaboo that I'm not telling you about right now that complicates this story. But in any case, so here's the Kähler cone for this caveat, and then when I flop, I get to this other Kähler cone. And over here, I have some asymptotic boundary, and over here, I have an asymptotic boundary. So this is the whole extended Kähler cone. There's just one flop connecting these 2 identical caveats. So then I can, knowing the whole extended Kähler cone, I can write down the whole region of the dual coordinates. I mean, across when I say K check, I mean the region of dual coordinates for the whole extended Kähler cone. And again, it splits into 2 parts depending on where I was over here. But then this whole region is this shaded red and blue region over here. This happens to be, in this case, and this isn't an accident, this happens to be just the dual in the sense of a cone of the extended Kähler cone. Right, this line here is orthogonal to that line there, and this line here is orthogonal to that line there. So you could also call this thing K star in this example, but more generally, the thing I told you about is this other definition. Okay, so now we want to know, are there infinite towers of BPS states everywhere in this K check region? So what I'm going to do is I'm going to compute the GV invariance. This is counting BPS states, at least counting them at large volume. And so it's a little bit funny because, you know, my table isn't really laid out on a grid. The LaTeX is doing some weird spacing here, so it doesn't look quite right. But in fact, the region K check that I had over here, I have to turn it upside down because the way the table is oriented, is the same with the same colors as this region over here. It covers all of these numbers that are not 0, except the 64 over here.
Benjamin,
so in fact, yes, go ahead.
May I just say time is running short now.
Okay, that's good because I'm almost done. Okay, good. Okay, so in fact, although we don't compute these arbitrarily far out, it does seem like every single number inside K check is non-zero. So there's a BPS state at every single site. Basically, the predictions of even the lattice weak gravity conjecture seem to be true in this example. So certainly sublattice and tower are true then. Now, we haven't proven that because we haven't computed the GV invariance arbitrarily far out, just as you see here. Okay, so what about this other number over here? These are hypermultiplets that become massless at the flop. There's in fact 64 of them in this example. So what about them? Why do they not come in infinite tower? Well, of course, the flow associated to these guys is bad, right? Because they become massless at the flop. So the central charge goes through 0. And of course, there's no BPS black hole associated to that. So kind of a picture, this is actually a different geometry, but one with similar properties. I didn't have the right picture, so I put this picture instead. It looks basically like this. This is very similar to the picture I showed you for heterotic string theory in a circle, except some of these lines are curved. It's slightly more complicated, but the qualitative features are the same, right? This is this state out here that comes just singly, and these are the extremal states that come in whole towers. Okay, so let me mention very quickly some other things I didn't have time to tell you about. So one thing is that you can check that the GV invariants fill out this K-check in many other examples, and this is something that Tom and the Cornell group are working on. So I'll leave it to them to explain more fully what they've done. Also, there's an interesting fact, which is, again, at least in a large class of examples, K-check turns out to be dual to the cone of effective divisors. And this is one way that you can, in fact, compute what the effective cone is by computing K-check. So that's kind of an interesting side effect of this analysis. I didn't have time to explain why this is true, but we could talk about it. The other thing that kind of the skeleton in the closet that I didn't talk about is what I might call ugly flows. Those are flows that end at a strongly coupled finite distance boundary in the moduli space. And the problem is that since effective field theory then breaks down, we don't really understand what happens then, whether there are in fact black holes like that or not. It's not that gravity, not that gravity breaks down, it's that you have some CFT appearing there. Okay, so I'll end there.
All right, very good. Thank you very much, Benjamin. That was a very nice presentation. And indeed, we have still time for questions. So do I see, I think Kumrun, do you want to ask a question? I saw your hand.
I didn't have a question. I was just clapping.
Okay, it was clapping. Yeah, sorry. Yeah. Sometimes clapping looks similar as raising hand for a question. But I think Timo has a real question, I believe.
Yes. Hi, Ben. Great
Hi.
talk. Thank you. Is it correct to say that the tower appears if and only if the gauge group can become extremely weakly coupled? Is this a correct summary of, or is this consistent? Are these two statements consistent? So one could also have said a tower must appear if and only if G and Mills can go to 0. Is this equivalent to the statement you're finding?
That's a good question, and I'm not sure of the answer on the top of my head. I don't know, Tom, if you have thought about that.
I haven't, no.
Yeah,
Because it
I'd
seems
have to look into that, yeah.
So whenever you have these flops, something can something is vanishing at finite rather than infinite distance. So and certainly the example of the conifold is such that you cannot take that limit for the particular gauge group that you're looking at for this particular direction, precisely because it is related to a flop transition rather than to a vanishing of a curve at infinite distance. So
yeah. Like I said, there are some interesting complications with boundaries at finite distance that I didn't get a chance to go into.
Okay.
So I'm not really sure, but that's an interesting question. I'll have to think about it. Thanks.
Thank you.
Good. I think the next question is then by Federico.
My question is, do you have any case in which the genus 0 Gopok-Mark-Vafa invariants inside the K-check are vanishing, and maybe it will be some higher genus Gopok-Mark-Vafa invariant providing
I don't think so. Tom, do you have any examples like that? I don't think so, though.
I'm asking this because recently we computed the explicit database of the genus 0 Gopok-Mark-Vafa invariants for complete intersection Calabi-Gauss up to a given cutoff degree. And we looked at something similar to what you're doing, and we don't find any case in which genus 0 Gopok-Mark-Vafa invariants are non-vanishing inside K-check.
You don't find any case where they're non-vanishing or where they're vanishing?
I don't find any case in which they are vanishing inside K-check.
Which they're vanishing. Yeah, I don't know any example like that either.
I think we actually have seen. Okay, so I'm actually not sure if it's in K-check specifically, but there are instances where the genus 0 Gopok-Mark-Vafa invariants in a particular direction vanish, but the higher genus ones do not necessarily vanish. I've not yet understood whether that's in K-check or if that's in so which region exactly that's in, but it's a possibility that does arise.
Yeah, we observe, of course, directions in the Picard lattice where the genus 0 eventually will vanish, but I think they are not direction inside K-check.
Yeah, that's very possible. Yeah.
Okay, thank you. Very interesting.
So are there more questions? comments? Apparently not. So we should thank our CLAP again for this nice presentation.